Okay, so where we left off was we had decided that we could draw into a unit circle 4 unique angles of rotation, one that started on the positive x-axis and was acute, one that started on the positive x-axis and went into quadrant 2, one that started on the positive x-axis and went into quadrant 3, and one that started on the positive x-axis and went into quadrant 4. These 4 angles of rotation end up creating 4 congruent yet unique right triangles where theta is the interior of the bow ties. It is worth noting that theta always touches the x-axis. Theta never touches the y-axis. So recapping what we've already determined, we have said that for any point P on the unit circle, the x-coordinate of a point P is the cosine of theta. The y-coordinate of the point P is the sine of theta. And we can find the sine and cosine of theta on a unit circle along with the positive, negative signs of those values by using the right triangles that are created with angles of rotation in the bow tie. Now it's also worth noting that within each of those triangles, the tangent of theta would be the opposite, or y, over the adjacent, or x. So this is y, this is x, and tangent will become sine theta over cosine theta. So we're going to fill in the rest of the notes now. Point P will always be known as cos theta, comma sine theta. And if you have the angle, as we will in these next 4 examples, we can plug the angle into our calculator and calculate its cosine to find the x value and calculate its sine to find the y value. Having said that, if I wanted to know what point P was on the unit circle, given a theta or an angle named A with a value of 30 degrees, I could type into my calculator the cosine of 30 degrees. The cosine of 30 degrees is 0.8660, and that would become my x-coordinate. Then I would type in the sine of 30 degrees. The sine of 30 degrees is 0.5. That would become my y-coordinate. The same thing is true for an angle of 45 degrees. P would be the cosine of 45 degrees, or 0.7071, followed by the sine of 45 degrees, which is also 0.7071. Would you please take a moment and calculate point P for an angle of 80 degrees and for an angle of negative 25 degrees? You should have gotten the following answers when you did those calculations. As I look at the 2 answers that I just calculated, it is worth noting that for this answer, which was an angle of negative 25 degrees, or an angle that would have started on the positive x-axis and rotated down into the 4th quadrant, that the x-coordinate or the cosine is positive, but the y-coordinate or the sine is negative. And that's, as we said before, because in the 4th quadrant, every angle will have a negative sign. To go in the opposite direction, if I have the point P and I want the angle, I actually have 2 choices. I know that this is the cosine of the angle that got me to point P named A, so I could write that the cosine of A is 1/2 and immediately invert it so that the inverse cosine of 1/2 is A. Or I could have written that the sine of A was rad 3 over 2. Immediately inverting that into the inverse sine of rad 3 over 2 is A. It really doesn't matter which of the two I choose. They will both give me the same angle measure. No matter whether I typed in this answer or this one, my angle would have been 60 degrees. This particular question, the next one, question B, has been rounded. So when you second cos 0.90631 or second sine 0.42262, your answers will be extraordinarily near each other but not quite exact because this point P has rounded values in it. Would you please pause the video and take a moment to try and find the angle given by the point in example B. What you should have gotten there is either that the inverse cos of 0.90631 gave you just a hair below 25 degrees, or that the inverse sine of 0.42262 gave you just a hair above 25 degrees. Either way, I would call that angle a 25-degree angle. Now, you might wonder how we would know some of these without a calculator, and the answer lies entirely within our special right triangles. So we're going to draw some of the original special right triangles that you would have learned a year or two ago, and we're going to relive them with a different pair of attributes. So this is a 30, 60, 90 triangle, and I'm going to pretend for argument's sake that this is a 45, 45, 90 triangle. It's just a hair off, but we'll live. In the 30, 60, 90 triangle, the ratio of the sides was always given as the shortest side was always going to be 1/2 of the hypotenuse and 1 rad 3 compared to the shortest side. So technically I should have x's on all of those, but you were probably taught to remember it as a 1, 2 rad 3 triangle. Now that's fine and dandy, except to apply it to a unit circle, keeping in mind that the hypotenuse and the radius are the same thing. The radius, which is the hypotenuse, would have had to have been a 1. So in order to use these values, I would need to proportionately divide everything by 2 so that my hypotenuse or my radius would be a 1. Likewise, in a 45, 45 degree triangle, my ratio of sides was originally 1x to rad 2 times x, where x is the length of the legs. And if I wanted to apply this into a special right triangle, values in a unit circle, I would need this hypotenuse to be a 1, so I'd need to divide all 3 ratios by a rad 2. I'm immediately going to rationalize that. And now I'm going to draw them into a unit circle. I'll draw 2 separate unit circles so that you can see them. And this unit circle, will have in it a 45-degree triangle. And again, And this unit circle will have in it a 30, 60, 90 degree triangle. Maybe I'll even draw 3, and that way you can see the 30 and the 60. So I'm going to group them so that I can move them all together. And then I'll just copy them so that I don't need to draw another one. Okay, so in this triangle, a 45, 45, 90, this is now a rad 2 over 2. This is now a rad 2 over 2. And this is a 1. Point P would have the coordinates rad 2 over 2, comma, rad 2 over 2. Remember that the angle I was using here was a 45-degree angle. In this special right triangle, I'll draw in a 30, 60, 90, where the 30 is at the origin. And in this right triangle, the one just above it, the vertical side is a 1/2, the horizontal side is a rad 3/2, and the hypotenuse or the radius would be a 1. So that the coordinates of point P would be rad 3/2, comma 1/2. And finally, in this triangle, I'll make the angle a little bit taller so that the 30 degrees is up here, which means that the 60-degree angle is down here. And instead of the 1/2 being the vertical side, in this case the 1/2 is the horizontal side. Rad 3/2 is the vertical side, and the coordinates of point P would be 1/2, comma rad 3/2. Now, using what we learned on the first page, that means to us that for a 45-degree angle, the cosine of 45 degrees is rad 2/2. The sine of 45 degrees is rad 2/2. The cosine of 30 degrees is rad 3/2. The sine of 30 degrees is 1/2. The cosine of 60 degrees is 1/2. And the sine of 60 degrees is rad 3/2. What we're going to do is we're going to put those all in a chart that we can memorize. And I'm taking these straight from the circles you just copied. Feel free to rewind if you need to see them again. But the sine of 30 is a 1/2. The cos of 30 is a rad 3/2. The sine of 60 is the rad 3/2 value, which goes along with what we said on day 1, that the sine of 30 and the cosine of its corresponding other acute angle in a right triangle would always be the same. So you'll notice that these two will match and these two will match. The cosine of 45 degrees is a rad 2/2, and the sine of 45 degrees is a rad 2/2. Now, keeping in mind that tangent was defined to be sine over cosine, I can get the tangent value by taking that 1/2 value and putting it on top of the rad 3/2 value. That's a complex fraction that has a common denominator. Those denominators will collapse, as we learned in Unit 1, giving me a value of 1/rad 3. Rationalizing that value makes it a final value of rad 3/3. Likewise, if I did the same thing here, sine over cosine would become rad 3/2 over 1/2. Collapsing the denominators gives me a value of just rad 3. And in the final example, sine over cosine becomes rad 2/2 over rad 2/2, which is a value of 1. These are the exact values for all special right triangles drawn into a unit circle in the first quadrant. You should memorize them. In our next section, we're just going to recap what we said in the first video, and that is that any point in this quadrant of a unit circle will have a point value that moves right and up or is a positive motion. What that means is that the cosine, which comes from the x coordinate, will be a positive valued answer. The sine, which comes from the y coordinate, will be a positive valued answer. And the tangent, which comes from y over x, will be a positive valued answer. In English, all three trig functions will be positive in quadrant 1. Any angle that you take the sine, cosine, or tangent of in the first quadrant